The objective of this lab is to learn how to use the diffraction pattern to measure the spacing of the data tracks on CDs and DVDs to see which disc format will have the greater spacing. The materials used in this experiment include a laser pointer with the known wavelength, a CD, a DVD, a protractor, an index card, several pieces of thin cardboard, a sturdy box, a rod and a stand, different color markers, a calculator, and a smartphone camera. To set up this experiment, place the CD label side down near the center of the workplace. Tape pieces of cardboard to the protractor so the laser can shine behind it. Tape the protractor flush at the bottom of the index card. Then tape the index card to the side of the box. The index card and protractor should be flush with the bottom of the box. Place the box over the CD. Line up the box so that the center of the protractor is lined up midway between the center and rim of the CD. Attach the laser to a rod stand and adjust the laser accordingly. Shine the laser and fiddle with it until a diffraction pattern is shown. Try to keep the beam as close to parallel with the card as possible. In order to make measurements, mark the locations of the incident and diffracted beams with a marker. Then find out the angles of the different orders of magnitude. After this is done, repeat this procedure with the DVD to compare it with the results of a CD.
What we found out from our data analysis in the first trough of the DVD was that when the incident rate was at 57 degrees and 106 degrees, the fringe at m equals 1 was at a distance of 12.949 Newton nanometers. Second fringe, it was at a distance of 19.24 nanometers. What we found out from our data analysis in the second trough of the CD was that when the incident ray was at 40 degrees and 70 degrees, the fringe at m equals 1 was at a distance of 21.17 nanometers. What we found out from our data analysis in the first trough of the DVD was that when the incident ray was at 57 degrees and 106 degrees, the fringe at m equals 1 was at a distance of 12.959 nanometers. What we found out from our data analysis in the second trough of the DVD was that when the incident ray was at 42 degrees, 90 degrees, the fringe at m equals 1 was at a distance of 13.23 nanometers. One of the most important topics of this lab has to do with diffraction, a type of interference where light bends around the corners of an obstacle. It is seen in this lab as the regular spacing of the spiral tracks, which explains how we found the D values. This spacing causes the CD and DVD to shine when it's placed underneath as an external light source. What we also learned is that the path difference is proportional to the order fringe multiplied by the wavelength lambda. In addition, we noticed a relationship between the difference of the sine angle, one being the diffracted ray and the other the incidence ray, and its correlated D value by employing multiple trials, regardless of whether it was a CD or a DVD.